Next step of our limit journey here, and we're going to be talking about calculating limits and some of the techniques you can use. I want to reiterate that in the last video we talked about how the limit and the definition of it is that when you plug in these x values, getting progressively closer to some other value, we see that the y values approach some value as well. So in the last one, we used an XY chart and we just plugged in progressively smaller values. In this video, we'll see there's much better ways to do it than doing that. And so to start off, we're going to talk about these limit laws briefly. Um, I'll talk about them because they're not the most useful. You'll see with our direct substitution property, we don't worry about these too much. But the idea is limits, when you're taking them, have these neat properties here that make life a little bit easy. To motivate it, let me give you an example here of using the sum property. So I said, okay, calculate the limit of this guy here. Okay. In the last video, we talked about how if we were to do this, we would just plug in 4.9, 4.99, 4.999, and see if the y values approach something. Because right, the idea is we're seeing that as x gets really close to 5, what does y get close to? But that's a little slow, right? And you usually have to use a calculator because you're dealing with weird decimals. So we can do these other methods here. So let's talk about the sum rule here. That's the only one I'll go over in the limit laws here. The rest, I think you'll be able to figure out. The idea with the sum law is if I'm taking the limit of this guy here, I can really just do this instead. You'll see I'm breaking it up into that limit, and then I'll do minus. Looks like I'm also using the difference property here, but you'll get the idea. 4. So you can see all I did is just break it up into smaller limits. The idea is these ones here are going to be easier to calculate. At this point, though, how do you calculate it? Because we've been talking about that XY chart. That's slow, it'll work, but there's a better way to do it, and that is called direct substitution property. Direct substitution property. The idea with the direct substitution property is that your limit, for example, as x gets close to a of our function here, is simply equal to the function at that point, okay? And this is going to be a little tricky because we'll see some problems it works beautifully. So in this example up here, what it's saying is you can just plug in 5 into here. So that's going to be 2 times 5 squared minus 3 times 5 plus 4. Do a little bit of simplification here. That'll give me 39. And so that's what this limit up here is equal to, is 39. All I did was plug 5 into x's here and here. Okay. Let's go through another example here. Let's say it said calculate the limit of this guy here. X approaches -2 of x to the third plus 2x squared minus 1 over 5 minus 3x. So let's go back to that direct substitution property. It's saying, hey, if you can just find function value at that point, then you're good to go. So I'm going to go ahead and plug in -2 everywhere here. 2, -2. If we carry on through this calculation, this should give us, let's see, -1 over 11. And so that's our limit here, -1 over 11. So you can see it's pretty simple. We're just plugging in the value and it gives us what the limit is equal to. And so you're wondering like, hey, why don't we just do this every time? What's the point of the limit? We'll see that the direct substitution property doesn't always work. You'll notice on this side here, it's saying that you have to be able to plug in this value. For example, if it's just x on the bottom and you're doing the limit as it goes to 0, you're going to have issues because you're going to be dividing by 0. And let me motivate that with an example. So if we do this one right here, we're trying to find the limit as this for this guy's x goes to 1, x squared minus 1 over x minus 1. And so let's do our direct substitution here. It's going to be 1 squared minus 1 over 1 minus 1, 0 over 0. And this is an issue, right? The idea is when I plugged in 1 to this function, this is undefined. We can't divide by 0. If you plug this into a calculator, it's going to give you an error. Okay. And so this is when direct substitution fails. But even though it failed here, let me show you something we can do. This will be part of the technique, is that when direct substitution doesn't work like this, what you'll want to do is some algebra. So if we look at this here, right, we have x squared minus 1 over x minus 1. We could do some algebra here and simplify. So this would be, if I factor the top, x plus 1, x minus 1. The bottom is now x minus 1. So cool, we could do some canceling here. This can cancel out so long as x does not equal 1, which is fine for limits because we're approaching 1. We're not actually at 1. What this allows us to do is rewrite this function here as just x plus 1. And so now if we do direct substitution, we have 1 plus 1, and that's 2, right? And so this limit here is 2, okay? Like I said, the idea is you can always just plug in the value. If it gives you something like a dividing by 0, something weird like that, like square root of a negative, you should probably use some algebra to simplify it so that you can use direct substitution, okay? Let's do one more example here just to round it out of how this direct substitution works. Let's say they ask you to calculate this limit. Let's go to the limit, and we'll use h instead of x. You'll see this later on when we talk about our derivative definitions. Okay, so here's our limit. We're taking the limit of this guy here. Let's go ahead and just plug in and see what happens, right? Go for direct substitution. 3 plus 0 squared minus 9 over 0. Okay, it's going to be 9 minus 9 over 0. And look, we have issues, right? Undefined. And so when this happens, you just need to simplify. So let's take our function here. Let me go ahead and clean this up a bit because we already know it's undefined here. So let's do something new with it. Let's take the top and let's just multiply out that 3 plus h, right? That would be 9 plus 6h plus 9, or sorry, plus h squared minus 9 over h. So you can see all I did was just like I squared this here. Let's continue with this here. These 9's cancel out, right? So we're gonna have h squared plus 6h over h. Okay, I'm gonna factor in h out of the top. That. Okay, these cancel now. We have h plus 6. Remember, this only is the case if h doesn't equal 0. And so we have this here now, which is fine. And so what we're really doing is we're finding the limit of this guy here. H plus 6, okay? Now let's plug in that 0, and we get 6. And that's our limit there. It's the limit of the original one up here. It's the same with our little simplified guy here. So just to reiterate where we are, right? In the previous video, we defined limits. We talked about how you could just use an XY chart to find the limit. It's really slow. It's not the best way to do it. So we're gonna, as we start diving into these algebraic ways, and we start with just the direct substitution property right here. Put a box around that. And this, keep in mind, this doesn't always work. There's a more formal definition, but the general rule I'll tell you is just plug in the value. If it gives you something, you're good to go. But if you get divided by 0, you have to do some algebra. So we showed 2 examples here where if you plug it in right away, you get a 0 over 0. And so what we did instead was simplify it first so that when we do plug in the value, we're good to go. So we'll wrap up there on this video. In the next one, we'll talk about some other interesting theorems you can use to calculate your limits.